Here we have an isothermal chip that is soldered to a heat sink. The dimensions and properties are as shown. The width of the chip as well as the heat sink it's attached to is 30. In fact, the area, not to scale, is 30 by 30. The length of the base, which is right here, is 4 millimeters. Each fin is 15 millimeters, and we have 6 fins whose thickness is 2 millimeters. Our surrounding temperature is 15 degrees C. The heat transfer coefficient is 150 watts per meter squared K. The conductive heat transfer coefficient, K, is 125 watts per meter K. And we have a contact resistance of 2 times 10 to the minus 6 meters squared K divided by W. And this contact resistance is caused by the chip being soldered to the heat sink. And what we want to know is if the maximum allowable chip power is 35 watts, what is the maximum temperature for the chip? So our governing equation is that Q sub C is the temperature of the chip minus the temperature infinity, T infinity, divided by the sum of the total resistance. Or we can write this, T sub C is Q sub C times R total plus T infinity. So we have everything that we need except for that total resistance. And what does that total resistance consist of? So this total resistance consists of the resistance because of the contact between the chip and the base, as well as the resistance of the base itself, plus this overall resistance that takes into account the fins. So let's start with our contact resistance. So our contact resistance is just the contact resistance per meter squared divided by the area, which is W squared. Our resistance for the base is just the length of the base divided by K times W squared. And finally, our overall resistance for the array is 1 divided by this eta sub 0 times H times the total area that it works on. So let's start with this last term. In order to solve for it, we have to find this eta sub O. So that's our 1 minus the number of fins times the area of a fin divided by this total area times 1 minus eta sub F. And this is for a rectangular fin. So let's do the areas first. So our total area is N, number of fins, times the area of a fin plus the area of the base, which is the exposed base. In other words, we have to subtract from the area of the base the area that the fins themselves take up. So the area of the fin is 2 times W times the corrected length of a fin, and the corrected length of a fin is L plus the thickness divided by 2, which is 0.016 meters. Next, let's calculate that area of a fin, which is 9.45 times 10 to the minus 4th meters. The area of the exposed base, which can be calculated as W squared minus the number of fins, their thickness times W. And when we calculate the area of the exposed base, it's 6.3 times 10 to the minus fourth. Now, from that, we can calculate our total area, where our total area is, again, the number of fins times its area plus that of the exposed base, which ends up being 6.3 times 10 to the minus 3 meters. Now, the next thing we have to do is calculate this eta sub f, which is the hyperbolic tangent of m times L sub c divided by m times L sub c. So what we need next is this m, which is just 2 times h divided by k times t, all raised to the 1/2, which equals 40. Therefore, our m times L sub c equals 0.63. When we put that into the equation for our eta sub f, we get 0.886, and now we have everything that we need to solve for eta sub 0, which again is 1 minus the number of fins times the area of the fin divided by the total area, 1 minus eta sub f. And when we calculate that, we end up with 0.897. So now it's time to start putting things together to find that total resistance. So this overall resistance from the array is 1 divided by this eta sub 0, or O, that we just calculated, times H times the total area, which equals 1.179. So let's put in our other resistances. So our contact resistance, which is the number that we were given, divided by W squared, is 0.0022. Our resistance of the base, which is L sub B divided by K times W squared, is 0.036. So now we put those all together. Our total resistance is equal to 1.182. And if you're wondering what those units are, they're K divided by W. Note how much of the resistance, in fact, the bulk of the resistance, is caused by the heat sink itself. So now we can solve for that maximum temperature. And that equals 35 watts times 1.182. And degrees K and degrees Celsius are the same. So we can say degrees C divided by W plus 15 degrees C, and our maximum temperature is 57.6 degrees C.